Hello and welcome to 1-1 Graphs of Equations. We're going to mostly focus on goal 1 here. We're not really going to talk about equations of circles today or graphs and applications. Those are some things that we'll hit later in the unit. So, equations in two variables. We often consider it y with respect to x, where x is our independent variable and y is our dependent variable. Also, if you want to think about it, x is the input where y is the output. Now, if we're given ordered pairs, and in order to satisfy if the equation holds, we have to recognize that this is the x-coordinate and this is the y-coordinate. We can directly substitute, and if the equality holds, we should be fine. So we can try 13. Does it equal 10 times 2 minus 7? 10 times 2 would be 20, minus 7 is 13. Goodness gracious. Cancel. 13 equals 13, so I would say yes. But if I were to try it with -1, 3, 3 does it equal 10 times -1 minus 7? 10 times -1 would be -10, minus 7 is -17. That obviously doesn't equal 3, so this one would not satisfy that equality. The collection of all solution points creates a graph. So if I were to graph all these, 2, -13, let's say is for the sake of argument, somewhere right on there. 3, 23, right about there. 4, 33, right about there. -1, 17, right about there. That's probably a little too far for -1. Somewhere right around there. 0, -7, right around there. Now, ideally, we would recognize the shape here. If we had actual grids, it'd probably show up a little bit easier. It looks like we're going up by 10 every single time. So theoretically, we'd also get the coordinate 1, 3. And if we subtract 3, we do 3 minus 10, we'd get -7. So ideally, if I drew this correctly, it should be a line. So let's just adjust a little bit so angle it a little bit better. Close enough. Now, it's important to note that in a line like this, the arrows would go on forever. So technically speaking, how many potential solutions would we have that satisfy this equation? Well, that'd be an infinite number of solutions. Let's say I'm sketching a graph from an equation, so I have some sort of equation. Let's say for the sake of argument, this is like y equals 2x plus 4. So I could create an input-output table where I have my x values, I have my y values, and then I have an x comma y. And let's say I pick an x value like, this looks like, I don't know, -1. I can plug -1 into the equation. So 2 times -1 would be -2, plus 4 would give me 2. So I would plot the coordinate -1, 2. So here we get -1, 2. We could then plot another x value like 0, plug 0 in for x. 2 times 0 is 0, plus 4 is 4. So I get the coordinate 0, 4, which is right here, 0, 4. And I could go on that process. Again, it's linear in nature, so it would keep going forever, and again, have an infinite number of solutions. So that's what I'm talking about with an input-output table. Some x value you're plugging in, your output, you get your y value, and then that coordinate. Recognize patterns, we can clearly see this is linear in nature, which makes sense from the equation. If I don't have an equation, I have to understand the shape of this. This looks like a U shape, so I would say this would be parabolic in nature or a quadratic. So it has to have some sort of x squared component. Now, we're not going to talk about transformations a lot, but I could see that normally y equals x squared looks like this from the origin, but my vertex is not in the origin, it's right there. So I could see that I have somehow shifted to the right a little bit and up a little bit. So the equation would probably look something like this. But we're not going to really expect that quite yet. We'll hit transformations later in the year, but those are just some things to keep in mind. A quick refresher, when things happen inside the function, so in this case, inside the parentheses, that moves it left and right and always opposite. So I went to the right one, so I did -1. And when things happen on the outside, it's a vertical shift, and it's normal, so up one there. Some other important things are x-intercepts. X-intercept is where it touches the x-axis, and important to remember, the y value is always 0. So that occurs here, here, and here. One thing to note is this is also an x and y intercept because it's at the origin. It gets both. Whereas a y-intercept, that's the y-axis, and the x value is 0, which we see right there and right there. Okay, find all the x and y intercepts. We get here and here, so that's 2, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10, 0. Oop. So those are my x-intercepts. And my y-intercept would be 0, -2. Here I get a y-intercept at -2, sorry, 0, -2. And I get an x-intercept right here actually at 8, 0. Now, I included the equation here because, well, two things. One, it's kind of murky to tell exactly where the intercept is, and it's easy to prove the extra conceptual point. So remember, if I'm looking for an x-intercept, I know that the y value has to be 0. So I can plug in y equals 0 into my equation to solve for my x-intercept. So I get 0 equals square root of x plus 1 minus 3, and I can solve for x. So we can add 3, 3 equals square root x plus 1, square both sides, 9 equals x plus 1, minus 1, x equals 8, which is exactly what we showed right there. This last one, we can clearly see there are no x-intercepts, which is perfectly fine. This is a quadratic, so it'd be a squared. This one would have no real solutions as well, so it would create imaginary solutions. But then we get a y-intercept at 0, 12. The last thing we're going to talk about is symmetry. Symmetry, for example, if it's symmetrical across the x-axis, the y values can be flipped. So if I have 4, 2, I also get 4, -2, because I can mirror using the x-axis. Symmetrical across the y-axis does the exact same thing, but the x values can be flipped. So -2, 4, and +2, 4. And then the origin, so the y symmetry is right here. And the origin means it's symmetrical around this point. So this would get rotated 180 degrees. So this becomes right here. And this becomes right here, kind of. And what happens there graphically is both my coordinates get flipped. Well, what are some easy equations that we could recognize this happening? Well, let's start with the y-axis one, because this one looks very similar. That'd be like a y equals x squared. And conceptually speaking, it should make sense that the polarity of x doesn't really matter. For example, if I did y equals -3 squared, and if I did y equals 3 squared, 3 squared, we all agree, is 9, and negative 3 times negative 3 is also 9. So that means that even if I have a positive x or a positive x or a negative x, it doesn't matter in the context of it. Both, for example here, negative 2 and positive 2, lead to the same solution. So using that knowledge, we can kind of construct one that would apply the inverse up here. That'd be like x equals y squared. The goofy thing is that's a little bit harder to graph for a couple reasons. One, if I go to my graphing calculator and I go to y equals, I can't solve or I can't change the y equals. So I can't make it y squared. And the reason that is because fundamentally, you're not going to need to know this for now, but it's going to help down the line. This actually isn't a function. It fails the vertical line test. So what we have to do is, one, solve for y. So how would I get y by itself here? Well, naturally, we would square root both sides. So we get y equals the square root of x. But if I graph y equals the square root of x, I'm in a bad window, zoom 6, I get the top half of it. I just get this part right here. Y equals the square root of x. Well, as it turns out, I can't get the bottom part because that would fail the vertical line test, which means this whole thing is not, or can't be one function. However, that does not mean the whole thing can't be two different functions. Now remember, we square rooted manually. What do we have to consider when we square root manually? We have to consider positive and negative. So I'm just going to graph y equals negative square root of x as a separate function. For the negative, second, insert negative graph. And that gives me the negative portion of it. So that is y equals negative square root x. So this one has to be approximated in a graph with two functions, but everything else stays the same. For example, if I did the square root of x, square root of 4, that would give me 2. If I did the square root of 4 to give me 2, but then I put a negative at the end, that would give me the negative 2 component as well. Origin's a little trickier. Some really easy examples would be y equals x and y equals x cubed. So those look like this. Y equals x is naturally just a line with an intercept of 0. And y equals x cubed looks like this. We can see that those patterns are the same in the bottom left quadrant as well as the top right quadrant. Well, how do we determine symmetry? Well, in order to determine symmetry, we replace, for the x-axis, replace y with negative y. So the times I would do this is when y has an even exponent. So this squared component. As we talked about more in depth earlier, for example, in the y-axis, it doesn't matter if I have a negative 3 or a positive 3 that I'm squaring, because negative times a negative is a positive, and positive times a positive is a positive. So that'd be the first test I would look at. If I'm testing y-axis, I flip the x's. I would often do this when x has an even exponent. And then origin symmetry, you actually flip both. And I would do this when they both have an odd exponent. So in order to prove symmetry, you typically just need to prove one of them because the kind of stuff we're doing right now is only going to have one of them. We will eventually get to things that have multiple, such as, for example, this is going to be a bad example, but we have what's called a rose. A rose looks like this graphically. We're going to pretend that all these petals are equal as well. It's called a rose because it pulls it like a flower, but you could see that that'd be symmetrical vertically, horizontally, and rotationally. So that would actually have all three different types of symmetries, but the stuff we're going to talk about won't. So we just need to prove one test. If you fail on a test, try another one. If you get none, that's okay. No symmetry. That is technically possible. So, test for symmetry. Here, I'm seeing that both have an odd exponent. If there's no exponent, it's 1. So the first thing I would test would be origin, which means I flip both. So I get negative y equals 2 times negative x cubed. Negative x cubed is negative x times negative x times negative x. So I'm multiplying three negatives together. That's going to leave me negative. And then, of course, I can divide both sides by negative 1. I get y equals 2x cubed. In order to prove for symmetry, after you do all the flips, this equation has to be the same as what I started. Those are the same, so I would say yes, this has origin symmetry. Here, I see that the y is squared, so I'm going to test x-axis. Oh, that's all I wanted. So I'm going to flip the y value. So I'm going to get negative y quantity squared equals 6 minus x. Negative y times negative y is positive y squared, which is exactly what I started with. So I'd say yes, this has x-axis. Here I see that the x is squared, so I'm going to test y-axis. So I'm going to get y equals 3 times negative x quantity squared plus 2 gives me y equals 3x squared plus 2 because negative x times negative x is positive x squared. It's exactly what I started with, so I'd say yes, this has y-axis symmetry. Thank you for listening, and I hope you have a great day.